Hello, everyone. I'd first like to thank you all for attending our talk. The title of our talk is Exploiting CSP in WebKit to Break Authentication and Authorization. Now, have you ever had an access to a zero-day bug which you could possibly use to take over accounts on any platform you want? Well, we kinda did. Today in this talk, we'll talk about a bug that enabled us to take over user accounts on most of the web applications out there. But first, a little bit about us. My name is Sachin Thakuri, and I am a co-founder and security engineer at Threatnics, where I do mostly web and mobile security stuff. And I'm also a co-founder of ThreatCon, a security conference based in Nepal.
Hi, I'm Prakash. I'm also a co-founder and a security engineer at Threatnics, where I spend most of my time hacking web applications and sometimes playing with JavaScript and new browser APIs.
Before we move on deep into the presentation, here's a quick TLDR version of the talk. Long story short, today we'll discuss a vulnerability that was reported to Apple that Apple didn't consider severe enough to fix quickly, which then, after waiting for a significant amount of time, we decided to exploit and earn some bounties by reporting them to confounded programs. The bug was in CSP implementation of WebKit, a browser engine used by Safari web browser, as well as all iOS web browsers, including Firefox and Chrome. The failure of WebKit to adhere to W3C specification when a CSP violation event is triggered leaked cross-site destination URI while redirecting from one origin to a different one. Combine this with common practice of implementing SSOs cross-site redirects to authenticate and authorize, we were able to steal codes, access token, or any other secrets that were part of the leaked URI, which we could then further use arbitrarily. This allowed us to carry out attacks, including but not limited to account takeovers, CSRF, and sensitive information disclosure. Moving on, now we will discuss few technologies and concepts before moving on to the vulnerability itself. SSO. Have you ever seen these buttons where you can log in using Facebook or Google accounts on a third-party website and wonder how this works? These features work through a technology known as SSO. Single sign-on, also commonly known as SSO, is a technology that provides centralized authentication service. Generally, users are asked to provide their single set of credentials, and authentication to all other applications are verified through a centralized authentication service. Its ease of use and effectiveness has made SSO really popular among modern applications. In addition to being simple and easy to use, SSO is also considered more secure. SSO commonly works by generating an authentication token, which is then passed to other applications and services. Authentication token then enables services to verify and authorize an identity, which is why securing and making sure that authentication token are kept safely is of utmost importance.
Well, I assume we all know what CSP is, but let's just revisit very quickly. Continuity policy, or CSP, is a set of policy or rules defining how browsers should load resources like JavaScript, CSS, or images, and whether to allow or deny execution of sets. It's defined using an HTTP response header called continuity policy, like some here, or using meta tag with some exclusions like report URI or fragment issues. CSP has been around since 2010 and is now supported by all modern browsers. We can also see it being widely implemented in Web 2.0 apps and a lot of improvements happening over the years. Though setting the CSP header still seems to be a hard task because it depends on resources used by each particular page or site. That's probably why there is not something as a default policy. I think it's not that uncommon to make mistakes while implementing a continuity policy. And for that reason, we also have something called continuity policy report only header. And what it does is, instead of actually executing the policy in action, it only reports violations, which makes it easier to debug if a policy is working as intended or not, without breaking anything. I guess we all must have seen CSP errors in our browsers and so on. So when it comes to CSP, we always have what we call violation reports, because what if a user tries to load a restricted resource, right? In that case, browse bulky request and dispatch a violation report. There are currently 4 ways to get a dispatch report: CSP's report URI directive, report to, voting observer, and security policy violation event. Throughout the talk, we'll be using security policy violation event for easier understanding. The report in general contains information on what caused the violation, like violated directive, original policy, blocked URI, the user, or the URI the user requested, and so on. Yes, it discloses the URL the user requested or tried to load, and that could be something sensitive if it is a result of a redirect. For example, in case of OAuth. So to avoid leaking sensitive information, W3C recommends user agents only include the URL of the original request. The image here at the bottom is from CSP 1.0 candidate recommendation from 2012, and even then we had such cases covered. It says the violation reporting mechanism has been designed in a way to mitigate such the possibilities of probing the behavior of non-server. And it also explains why. That is, if violation reports contain the full blocked URL, the report might contain sensitive information contained in the redirected URI, such as session identifiers. And as Sachin already said, it's pretty common in case of SSOs and OAuths, for example. However, it recommends including the origin of the blocked URI, which is still an issue, and we have a long history of reports on that. We found a few disclosure reports on Chromium tissues leaking origin of blocked URI in one way or another using CSP. All these reports share the same problem, the leakage of cross-origin redirect URL. Thus, we'll only talk about the first one from 2013 by Igor when CSP was still in its infancy. He demonstrated what we could achieve by using CSP's blocked URI directive. Remember what W3C said in its recommendation? Well, this has been coded directly from his blog post where he says, we can use CSP tree to detect if a user has authorized certain apps or clients, because all authorized apps will redirect to the home page instead of login or authorization page. For example, if you have already authorized Instagram on your Facebook, sending a request to Facebook auth endpoint for Instagram would redirect to Instagram instead of Facebook. We also found reports leaking full block URI in 2020, which are very similar to ours that we'll talk about shortly.
Now, after that history, let's discuss the root cause of the vulnerability. We can define a CSP policy in such a way that whenever a redirect happens to a domain with different origin, also known as cross origin, a CSP violation occurs and a security policy violation event is fired. As you can see in this figure, our domain cm2.pw with described CSP policy makes a fetch request to domain1.com. Then the response header from domain1.com contains a location header that now redirects to a domain with different origin, domain2.com. But due to our CSP policy, the request to domain2.com is blocked and a CSP violation event is fired. Now, when security policy violation event is fired, it uses security policy violation event interface target with different attributes. And while setting values for these attributes, a failure by WebKit to adhere to W3C specification resulted in leaking 3OX redirection location in document URI attribute. As you can see in the example, fb.com/secret here redirects to facebook.com/secret here. Then you can see difference in values for attribute document URI set by Safari and other web browsers, while other browsers who have followed specification mentioned by W3C seems to set value of a URI with values from where original fetch request was made. Safari, who failed to follow the W3C specification, set those values with final redirection URI. Now, you might be wondering, how can this be exploited in SSO? As you can see in this figure here, when a user loads example.com, it first checks if the user is authenticated or not. And if the user is not authenticated, then as shown in the figure, it will send the user to auth.example.com, which is a SSO domain that provides centralized authentication. Now, after verifying the user is then redirected back to example.com with an authentication token. Now, The general common practice while implementing SSO is to use different subdomain or an entirely different domain, which then doesn't meet the criteria to be defined as same origin. So the final redirection that happens from SSO domain to the final domain, or in the case as shown in the figure from auth.example.com to example.com will be cross origin, thus allowing an attacker to steal the final redirection URL. In today's modern application where authentication and authorization are heavily dependent on technologies such as OAuth, SSO, and JWT, where secrets are passed through URLs, the leak of the final redirection URI made application using these technologies almost always vulnerable.
The responsible disclosure didn't go at default, it did. We first reported the vulnerability to Safari in February 2020 and had to wait for a few weeks before we even received an automatic acknowledgement. After 2 months of waiting, we finally received a reply on April 20, and to our surprise, it said, "This doesn't seem to pose a threat to WebKit users." They further went on to explain that even after fixing the issue, an attacker could gather the same information by monitoring WebKit logs while running an attacker control build of WebKit. To us, it seemed as if they failed to understand the vulnerability and the risk it posed. Trying to convince them, the time went by, but we saw no progress at all. So in January of 2021, after waiting for almost a year, we decided to explore the potential of the vulnerability in the wild by targeting bug bounty programs. The exploit was simple. We set up a page with CSP, as shown in the slide here, which is the domain which we are sending requests to, add an event listener for security policy violation, and send the request. Sending a request to an authorization endpoint issues a redirect to another domain with code or token appended to the URL, which is typically the case for OAuth or SSOs, whereas the policy only allows loading of resources from the page itself and the domain specified, or after example.com here. So as Sachin said earlier, an attempt to load resources from any of the domains would violate the policy and trigger the security policy violation event. The document URI then would have this value of the actual block URI and not just the origin. We've also prepared a playground for everyone to make it easier to experiment with the vulnerability. The usage is as simple and pretty straightforward. We pass in a number of parameters as shown in the usage on the left, and the page then sets a prepared continuity policy using the domain truncated string and displays the to-do as shown on the right. There we have added an exploit button as a workaround for ITP, which Sachin will explain a little later. And after a little bit, it issues a fetch request to the URL specified in the query string, which redirects to another domain, causing a CSP violation. The event listener would then print a secret on the screen. The source code is also available in GitHub, so feel free to use as you please, for tweak or contribute however you want.
We have a short demo here. In this demo, we'll demonstrate how an attacker can use this vulnerability to take over Instagram accounts. So the attacker will first get the OAuth URL to get the nonce and state values. So basically what an attacker is trying to do is trying to create a URL that will be sent to the victim. So yeah, so the attacker will copy the full OAuth endpoint URL with nonce and state value. Then that particular URL will be sent to the victim. Whenever the victim visits our POC URL, So whenever the victim visits our POC URL and somehow interacts with it, the access tokens of that particular users will be leaked, that then the attacker will use to logging into victim's account. So now you can see that the attacker is basically logged in as the victim. Okay, now after that demo, let's move on to the, let's move on and discuss some impact. Yeah, it took us a while to understand the full impact the vulnerability had. The vulnerability did not just affect Safari browser, but because of the Apple's App Store policies that states that Apple apps that browse the web must use the iOS WebKit framework and WebKit JavaScript, which means that web browsers can implement their own rendering engines. They must embed a version of Safari's rendering engine, which made browsers like Firefox, Chrome, Opera in iOS devices vulnerable. And due to the nature of design of OAuth, almost every implementation of OAuth that exists were vulnerable. Using the bug, we could take over Facebook, Instagram, and WhatsApp accounts. The bug also affected Google's SSO, which means Google products using Google accounts. Central authentication were also vulnerable. Cryptocurrency platforms, social networking platforms, e-commerce platforms, and more. In today's modern application, it's very rare to find an application not using OAuth. So let's just say the numbers were very high. And since the vulnerability affected SSO, so it's obvious that different SSO providers were also affected by this. And many applications nowadays make use of login with third-party features, such as login with Facebook or Google, to provide the user with easy and seamless authentication experience. And since most of these features make use of OAuth, these applications implementing login with feature were also affected, thus allowing an attacker to take over accounts of platforms implementing these features. For example, if you have an e-commerce website where you have a feature that allows users to log in with Facebook account, then an attacker could basically take over accounts of your users in your e-commerce website by stealing Facebook OAuth tokens. Moving on, let's discuss some roadblocks and common misunderstandings that we saw among security teams of different bug bounty programs. Starting with ITP. ITP, or Intelligent Tracking Prevention, is a privacy feature developed and implemented by WebKit, and it has been in use since October 2017. ITP uses machine learning model to detect cross-site tracking capabilities and aims to reduce them by taking different actions such as full third-party cookie blocking, reducing the accessibility and longevity of first-party cookies, local storage capping and deletion, downgrading third-party referrers, and more. Due to the nature of the attack, where it relied on making third-party requests, ITP rendered the attack unusable on latest versions of WebKit. According to documentation from WebKit, to circumvent it, there needs to be a user interaction. It could either be a tap, a click, or a use of the keyboard with your website as first party. So in a real attack scenario, we open up a tab using window.open, and then we keep calling the vulnerable endpoint until the user interacts with it. When we started submitting this vulnerability to several bug bounty programs, we noticed that a few of them had similar misunderstanding around them. A common misunderstanding among security teams of several programs was around authorization code, unaware about its capabilities and how sensitive it is. The misunderstanding was that without the ability to exchange authorization code for access tokens, the authorization code were useless, since exchanging them required application ID and application secret. While the statement above is true, in a case where OAuth was used for authentication, simply having an access to authorization code was enough to get access to victim's account. Making a request to an authorization endpoint with stolen authorization code with attacker-generated state or nonce value would allow an attacker to authenticate into a victim's account. And Another common misunderstanding was with regards to state or nonce value and its capabilities to prevent attacks in OAuth. While using state in OAuth is an excellent way to prevent CSRF attacks and to redirect users to where they were before the authentication process started, apart from that, the state really doesn't provide any additional security features. Even if the state value is bound to a token, an attacker can generate a fresh state value, which then can be attached to an OAuth endpoint URL to send to the victim. The resulting token of the request then can be used by an attacker without an issue. The same thing was also demonstrated in our demo of OAuth, where we saw that nonce value or state value did nothing to prevent the attack. Moving on, these are some of the stats based on bug bounty programs and reports we made. In total, we were able to harvest more than $100K in bounties, and the response from the bug bounty programs were kind of mixed. While some programs took the issue very seriously and applied a fix in under 21 hours, which was really impressive, some took months to just understand the vulnerability, and some of the programs also relied on WebKit to come up with a fix. Some programs like Dropbox and Polonix took it one step further by using their contacts at Apple and asking them to come up with a fix. The highest single reward was given by Coinbase, which was also the fastest program to fix the issue. And Apple took more than a year, a total of 457 days to come up with a fix. And in the end, decided that the bug does not qualify to be awarded a bounty because it does not meet the published bounty categories. And ironically, while this bug in WebKit made so many applications in the internet vulnerable, the Apple's implementation of SSO and OAuth were not vulnerable.
We saw how we can exploit the vulnerability and how severe it could be. Now, let's discuss some fixes as well. As a developer or a site owner, we can use any or a combination of these methods to prevent such vulnerabilities altogether. They're all very easy to understand and implement as well. The first one is to use post method instead of get, which actually aligns with the practice of never sending any sensitive information over the URL. For example, SAML, or security assertion markup language, already uses post instead of get for transferring tokens. The second one is to use post message for cross-domain communication. These two fixes are also supported by OAuth or OpenID Connect, as can be seen in the image on the right. They could be specified by a response underscore mode as long as the authorization server supports. However, it's still necessary to disable or remove the support for query and fragment modes. The most effective one, in my opinion, is the third one, same-side cookies. It not only protects against this particular vulnerability, but makes almost all kinds of vulnerabilities invisible. Same-side cookies also protected quite a few programs in our campaign. Now, similarly, we have Pixie for OAuth, which makes the exploit useless because we also need code verifier to make the use of leak code. And the other one is to ask for authorization every single time, also supported by OpenID using the prompt parameter. And Apple does the exact same, and others too. One can also use client-side redirects instead of 301 or 302 in combination with examples or CSVs from ancestors. Twitter, for example, uses this method of redirect, and many programs we reported the vulnerability to also fix the issue using this approach. The last one is to validate referrer or origin against the client, though we do not recommend using this approach as it suffers from the same issues as with CSRF protection with referrer or origin. There's also something called resource isolation policy, which uses face metadata, but unfortunately, Safari doesn't yet support them. Browsers also have some mitigations in place to avoid such leaks besides same origin policy. However, the strategies listed here are specific to CSP. We have something coming up that these strategies do not cover. For now, let's briefly go over them. The evaluation reports now include the URL of the original request, meaning we only get what we already know. Furthermore, browsers know the path component after resource extraction if the resource being loaded is the result of a redirect. This is to prevent leaking of path information, which was demonstrated in Prakash post. And this spec also gives an example for easier understanding. but we'll leave it at that. Well, we plan to release it as an OD back at Europe, but Apple fixed it right before our talk, and it no longer works in the latest version of Safari. But let's discuss it anyway, along with bypasses. After our reports, many programs, including Facebook and Coinbase, came up with their own fixes. And their fixes revolve around checking if the user agent is of Safari, and only if it is, they would use a different approach. For all other user agents, their workflow remains the same. So it seemed a simple change of user agent would bypass the fix, and an obvious place to try it was on iPhones or iPads, since all browsers on iOS devices must use WebKit as the engine. They're all essentially the same. Just using Chrome didn't work, but changing to desktop side did. However, the change of user agent wasn't inherited in subsequent fetch requests. So we tried all requests from a project called HTTP Links by Gear53 and found that aping or anchor with ping attribute did the work. We had another bypass, but during our hunt for bypasses, we noticed something peculiar. After some digging, we realized that we've already found another zero-day. And this time, it wasn't CSP, but cross-origin resource sharing occurs. The finding was as easy as shown here. We just needed to add a catch handler to our fetch request, and it disclosed the destination URL. We set our plan to disclose the vulnerability with Apple, and surprisingly, it got fixed right before our talk, without us ever being notified. And it turns out that other researchers had also found the same vulnerabilities. Our research paper was released a few days back on access to leaks, which also had these vulnerabilities in their test cases. And now the three key things to take away are same-site cookies can be super helpful to prevent any cross-site vulnerabilities. I use defense in depth to mitigate browser flaws instead of entirely relying on browsers, because browsers do not always follow the spec completely. With that, we're at the end of our presentation. Thank you for listening. We hope you enjoyed the talk. Thank you again.
Thank you.
Okay, thank you. So we're going to be taking a number of questions in the room, but there are already some questions coming from the IRC. So thank you for that interesting talk. And we got a question about the vulnerability that you found in WebKit. Is it also present in gaming consoles such as a Nintendo Switch or PlayStation? And has it been fixed?
Yes, since the vulnerability was in WebKit, so yeah, every gaming consoles or any other applications that made use of that particular WebKit version were vulnerable. But then in our test cases and different tests that we run, we did not check for those vulnerabilities in those gaming consoles. So we're not. But then since the new WebKit version that was released after we reported the vulnerability to Apple came with a fix. So if those gaming consoles updated their WebKit versions, then the bug is fixed there.
Okay. So got another question about at one point you mentioned that Coinbase and also Facebook paid a bounty, or maybe only Coinbase paid a bounty, but Facebook fixed the vulnerability, which means that they basically understood the vulnerability. But if the vuln was in the browser, were they able to fix it in an efficient and effective way?
Yeah, so I think we reported this particular issue to around 25 to 30 different programs, including Coinbase and Facebook, and almost out of 25 to 30, I guess almost 90% of those programs paid bounty to us. And then the Coinbase took the issue really seriously, and they knew that the vuln was in the browser itself, but there were different code changes that they could take, which would basically allow them to fix that vulnerability, although the vuln was dependent on browser. So yeah, we suggested them a few different approaches, that Prakash also discussed in his slides. And yeah, using those suggested fixes, Coinbase were able to fix the vulnerability. And in fact, both Coinbase and Facebook, they came up with a similar approach to fix the vulnerability, which was to first check if the user agent is from WebKit-based browsers, and if the request coming in is from WebKit-based browsers, then instead of doing 302 redirection, they implemented a client-side redirection that basically fixed the issue. So yeah. Both of these programs came up with their own fix, which was quite similar to each other. And they were able to fix the vulnerability in a really effective way.
Okay, even so, if you can easily change the user agent.
So yeah, so in that case, so one of our bypasses, I think Prakash would like to discuss it, like one of those bypasses in mobile desktop-based browsers. I think Prakash.
Yeah, actually, that's where we searched for bypasses, and then we found that changing to desktop agent would bypass the fix. But it kind of required it required quite an interaction. So it was like to bypass the ITP, it already required a click, and then to change user agent, that required another user interaction. So they decided not to fix it that way because it was also dependent on the browsers. So though they didn't fix it, the Safari fixed it, I think almost at the same time. So they decided not to make any further changes on their implementation. So it no longer works, and their fix is perfect so far, I think.
Okay, thank you. Are there any other questions? Apparently not. So thank you again.